From where? Okay. Yep. Oh.
So, hello everyone. The next talk is about Base64 is not encryption by Seth Bargo. Welcome.
Hi, everyone. Can everyone hear me? I'm a little sick, so awesome. I see a thumbs up in the back of the room. Welcome to Base64 is not encryption, or a better story for Kubernetes and secrets. My name is Seth Vargo. I'm a developer relations engineer at Google. Small company, probably haven't heard of them. And I only have 30 minutes, so I'm kind of going to run through this quickly. But if you have questions or if I say a word and you're not sure what it means, please come up to me afterwards and ask me, or feel free to tweet me. That's my Twitter handle. My direct messages are also open, so if you don't feel comfortable saying something publicly, you can always send me a private message, even if I don't follow you. All right, so let's set some ground rules here. What is a secret? Everyone kind of has their own definition. For the purpose of this talk, I'm going to define a secret as credentials, configurations, API keys, or other stuff that an application or service needs to run either at build time or at runtime. So when you compile the application or when it's running. And we're specifically talking about secrets in the context of Kubernetes, right? There have been a lot of other security talks. We're really just narrowing in on Kubernetes here. And then we kind of have to ask ourselves a really obvious question: why should we protect them? Why not just use a config map for everything? Why do we even have secrets? How do we separate secrets from configuration? Well, first, secrets are a really attractive target for attackers. They often are leaked in public repositories or open buckets on S3 or Google Cloud Storage. And they often include overly broad permissions, and they're often given to people who shouldn't have those permissions. Like the CEO of the company should not have sudo access to all of the machines, yet that's what happens. And these users tend to leak these credentials everywhere. So we need a really strong strategy for protecting secrets. There are really 4 ways in which we can protect secrets. We can audit them. So this is kind of retroactively. Let's log every use of a secret. Let's make sure that we can trace who's using a secret and when. Encryption in transit and at rest. Rotation, we know that it's not enough just to have a secret. That secret also has to have a lifetime. It can only live for a couple hours or a couple years. And isolation, right? That's kind of principle of least privilege, making sure that the place where secrets are accessed is not the same place that they're stored. This talk is really focusing on the encryption bit. That's really all we're going to talk about today. There are a lot of things that we could talk about, but we're kind of limited by time. So let's talk about encryption. There are 4 layers of encryption that are kind of common. The first is what we call application layer encryption. Application layer encryption I'll talk about in more detail on the next slide. Then we have service level encryption. File system encryption and machine level encryption. So machine level encryption is like where you have a hardware device like a TPU. Operating system encryption, something like BitLocker or File Vault on Mac or Windows. And then service level encryption is where you have some kind of like operating system level encryption. Application layer encryption is kind of the highest level of encryption that we have today because it's applied at the earliest possible step in the encryption process. And it provides encryption at a very granular level. So when you think about something like File Vault on OS X or BitLocker on Windows, that's a key that protects an entire file system. And if an attacker is able to get that key either through brute force or social engineering, they've decrypted the entire file system and all of the data is now available to them. Whereas if you imagine each file in that operating system is encrypted with a unique key, even if they're able to brute force the high-level operating system level key, they still need the lower-level encryption keys in order to access individual files, right? And this is really the context of application layer encryption, is that it doesn't just protect the data at rest, it also protects the data as it moves through the system. So again, taking that same example, if I have some file system level security like BitLocker or File Vault, if I take that file and move it to an NFS share, it's now available for anyone. It doesn't matter how secure my local file system is, I've moved it to an insecure store. However, if we were applying application layer encryption, I've instead moved a bunch of encrypted bytes from one file system onto another, and it still has the same level of security that it had before. So, application layer encryption is just one level of encryption, and generally we recommend using at least 2 layers of encryption. So you want to use application layer encryption to protect things at the most granular level, but then you also want to use file system encryption, encrypted backups, or even hardware level encryption with something like TPUs and secure boot. So, all of this background was to introduce you to Kubernetes defaults. So how many people here are familiar with Kubernetes? Cool, you're in the right room. How many people know why I have 4 frowny faces? Cool, you're about to learn. So Kubernetes is insecure by default. And there's a star there, which I'll explain in a second. But by default, when you spin up a new Kubernetes cluster, whether it's Minikube or kubadmin or localkube, all of the secrets are stored in plain text in etcd. Etcd is kind of, you can think of it as like the database that backs Kubernetes. It's a storage engine where most of the data is stored in memory, but they're only Base64 encoded. They're not encrypted, meaning anyone with access to etcd or a backup of etcd or the master node can actually retrieve every single Kubernetes secret and service account with a single request. Now, there is a star here, which is that a lot of providers, like cloud providers, will alter this default behavior. So if you're using like Google Kubernetes Engine or AKS or EKS, they don't do this by default. But if you're running your own Kubernetes cluster on your own bare metal, or you're using some type of virtualization where you're managing this yourself, if you haven't configured it, anyone with access to your etcd cluster or your master nodes has access to all of your secrets. So what does this actually look like? So here we have a piece of data, a credit card. And let's say I'm going to create this secret. So I'm going to run kubectl create secret with the contents of this particular credit card. That's going to hit the kube API server, and the kube API server is going to encode but not encrypt that data. See, it's encoded. It's just upside down with 2 equal signs at the end. I'm glad some of you got that joke, right? So if an attacker, which is represented by this raccoon on all of the slides, has access to that etcd cluster, all they have to do is turn that upside down and remove some equal signs, and they have your credit card data, right? And it can be a credit card, it can be a service account, a passport, a social security number, any type of secret, right? An API key, whatever it might be. I like to call this encryption. And I know what you're thinking, right? Number one, I'm not here to talk badly about the Kubernetes developers, right? Secrets were an afterthought, and that's okay, and we're working on it. Number two, you're probably thinking, well, no one is going to leave their etcd cluster publicly exposed, and I work for a company that doesn't let me show you this, but there's a URL, and I highly recommend that after this talk, you go ahead and take a look at how many etcd clusters are publicly accessible with no authentication. So instead of just talking about it, I figured I'd show you this. So let me jump out of the slides real quick and enter mirror mode. All right. So what I have here is I have a Minikube cluster because I wasn't sure how the internet was going to work, but this could also work on a big Kubernetes cluster. So I'm going to use the secrets default context here. And now I'm going to create a secret. So I'm going to say kubectl create secret generic. What should our secret be called? Demo? Okay, cool. Y'all are real exciting here. And our secret will be, I don't know, password equals FOSDEM. Encryption, okay. I type encryption so much, it's hard to type encryption. I can't type. Kubectl create secret generic. What did I type wrong? Oh, I spelled literal wrong. LIT, wait, what? You're right. I can type. There we go. Cool. So I've now created this secret. How many people feel secure? Cool. I'm going to make you feel even more insecure. So I'm going to cheat and exec right into the etcd cluster, but there's a number of different ways you could do this. So I'm now on the etcd node. This could be publicly exposed. This could be a backup that you have restored because someone accidentally uploaded it to an S3 bucket. Fun fact, that's what happened with Tesla. just restore it, point it to it, and you're good to go. So I'm going to run etcd cuddle get registry secrets. It's in the default namespace, and we called it demo. And look at that. Encryption is just like right there, just in plain text. You don't even need to use etcd cuddle. Like, you could just search the file system for this if you knew what you were looking for. So y'all should be real scared now. All right, so what can we do to fix this? Well, the first thing we can do is explain envelope encryption to you, because the rest of this talk won't make sense without talking about envelope encryption. So what is envelope encryption? Well, normally we have two pieces of data, a secret, like a piece of data, and a key. With envelope encryption, we introduce another kind of key. So we have two keys. We have a data encryption key, the thing that encrypts our data, and a key encryption key, the thing that encrypts the key that encrypts our data. It's very meta. So I prepared some animations for you, and I hope you're impressed. So seriously, this took forever. So we use our data encryption key, which is the red key on the slide, and we use it to encrypt our data, and that gives us some bytes. You can see that's denoted by the little red lock icon. Then we take our key encryption key, which is the green one over there on the right, and we encrypt our key with that key. So the actual bytes that encrypted our credit card are now encrypted using this other key. We then concatenate those two pieces of data together, and we store them side by side using some type of separator in our storage system, whether that's a database or a file system, mobile phone, whatever it might be. This is envelope encryption at a very, very high level. When we want the plain text data back, we reverse this whole process. So we separate the pieces based on our separator. We then use the key encryption key to decrypt the data encryption key, which we then use to decrypt the encrypted data to give us back the original plain text data. I hope you liked my animations. Every time we encrypt a new piece of data, we generate a data encryption key. That's usually the responsibility of the operating system or the software to generate this one-time key. So you generate some entropy, you generate a 32-bit key, or 32-byte key, you encrypt the data. The key encryption key, the things over here on the right, they tend to live a little bit longer. So a key encryption key might encrypt 5 or 6 or 100 different data encryption keys, or DECs as we call them, and we rotate them periodically. And we store the version number inside of here so we can easily decrypt them. So envelope encryption, we generally generate a unique DEC for each new data entry. We can crypto shred. If you don't know what that means, think GDPR. I have a bunch of data and I need it revoked immediately. Instead of zeroing out a bunch of data, we can just revoke the top level key encryption key, and now all of that data is irrecoverable except for brute force operations. Oops. And it provides easy versioning and rotation. We can rotate the key encryption keys and the data encryption keys separately. So we don't have to maintain all of these kind of keys running around. So Kubernetes 1.7 introduced envelope encryption to try to solve this problem. So there's this top level thing that you pass to the Kubernetes API server when you start it, called an encryption configuration. You give it the different providers you want, and there's a number of different providers, AES CBC 256, GCM 256, Secret Box, etc. You put the keys in this file, and then you restart the Kubernetes API server with this -- encryption -provider -config flag, and all is well. So it goes like this. So the data comes into the Kube API server. The data then goes to this encryption config first, before it goes to etcd. The encryption config encrypts it, and then puts it in etcd. Right? So we're secure, yay! This talk is over, except I have 15 minutes left. So what happens if an attacker has access to etcd? Well, they have some encrypted data. That's great. Like, they can't really do anything. They can brute force decrypt it, maybe, but hopefully we've rotated our secrets by then. But what happens if an attacker has access to our master node? So that encryption config lives in plain text on the master node, where the keys are. So any attacker worth their salt, no pun intended, can grab access to that encryption config file, which, if you remember from back here, has the keys in it. So all we've done is given a really, really big lull to a skilled attacker, because they're thinking, oh wow, you went to all of this effort and complicated your setup and added overhead only for me to just decrypt it with an OpenSSL command. Because the encryption keys and the encrypted data are stored in the same threat model. We haven't actually improved our security for anything other than a script kiddie. So there are a number of drawbacks to this approach. Number one, you have to generate those keys yourself. So anytime you want to rotate or manage keys, you have to generate them yourselves. So you need some type of entropy source. Key management is your responsibility. If you've ever actually done this, it's really a pain in the butt. You have to restart the Kube API server every time you add a new encryption key, which causes downtime or potential loss of service. Rotation is a manual process, so you have to decide when you rotate, how frequently you rotate for both the DEX and the KEX. And there's no HSM integration. So if you work in a large enterprise where you process credit cards or personal identifiable information, you can't integrate with an HSM this way, hardware security module. But kind of as we talked about, the biggest drawback is that it doesn't actually improve your security standpoint. The plain text encryption keys are sitting right alongside the encrypted data. So Kubernetes 1.10, we're on 1.13 now for those playing along at home, introduced some happy faces. So let me tell you how Kubernetes 1.10 makes this really great. Kubernetes 1.10 introduces this concept of a plugin for encryption. Particularly, it uses KMS plugins, or key management service, or key management provider plugins. They operate on a Unix socket, so you can leverage Unix file permissions to control access, and they delegate access to a key management service outside the management layer of Kubernetes. So it looks like this. The data comes in, it hits the Kube API server, it hits the encryption config, and then instead of hitting a local key, the encryption config uses that socket and some type of authentication to talk to an external KMS provider. Then encrypts the data in etcd. So if an attacker, and then to reverse the process, it has to go back to KMS to get you the plaintext data to go back. So if an attacker has access to the master node or etcd, they still don't have access to the keys because those are stored in a separate system. For example, that system might be something like Google Cloud KMS or Amazon KMS or even something like HashiCorp Vault. And there are existing plugins, KMS plugins for Kubernetes that do this for you. So if you want to take a picture of a slide, this is a good one. So there's one that will integrate with Google Cloud KMS. There's one that will integrate with Azure. I actually think Rita Zhang is here. She's done a ton of work on that and a bunch of other stuff with flex volumes. There's an AWS encryption provider, and there's one that I'll demo in a second, which is the Oracle Kubernetes Vault KMS plugin. If you're on Google Cloud, so if you're running on GKE, Google Kubernetes Engine, we actually have an option that will go into beta on Tuesday. It's in alpha right now, but you can still use it. That does this for you. So when you spin up a cluster or in the UI, you can specify a KMS key, and we'll set up all of this for you. So this is automatically done. We already do a bunch of stuff to protect the cluster. This gives you full control over the key and the rotation, and we'll do auto rotation of those keys for you. But it introduces a new problem, which is how do you authenticate your Kubernetes nodes to talk to the KMS provider? How do you, and it's called the initial secret problem or the first secret problem. And generally, IAM is the way that you do this if you're on a cloud provider. So identity and access management. On GCP, that's service accounts. On AWS, that's either ARNs or access tokens. But generally, you give the master node either a service account credential, an access token, or you grant the machine that it's running on permission to talk to the API, and you can revoke that at any time. So you delegate PAM to the cloud provider through IAM, and then you separate concerns. So the etcd nodes, the physical VMs that etcd is running on, does not get permission to talk to the KMS provider. You only give that to the API server nodes. And this separates concerns so that an attacker has to compromise multiple systems in order to decrypt these values, and you can revoke access to the KMS keys at any time. So what if you're not on a cloud provider? Or what if you already have a custom managed, Kubernetes setup and you're not ready to move to a cloud provider managed one where these plugins already exist? Well, this is where something like Vault can come in. So instead of the KMS provider being a third-party KMS provider like Google Cloud KMS, instead we can delegate this to Vault. And our friends over at Oracle have built a really helpful plugin that runs in Kubernetes that helps us delegate this encryption and decryption to Vault. Again, this is envelope encryption. So in Vault, there's this thing called the transit backend. It's basically key management as a service. Vault generates a key. Kubernetes then uses that key to encrypt another key, the data encryption key, which it uses to encrypt data at rest. So what does that look like? So let me jump back over here. My cheat sheet. All right, kubectl, config, use context. So we'll switch to a new Kubernetes cluster. This Kubernetes cluster has the Vault KMS encryption already set up and ready to go, and that encryption config. So I'm going to go ahead and create that same secret. And now when we exec into etcd, hopefully, etcd cuddle, get registry secrets default demo, you'll notice that that's not plain text anymore. That's a bunch of gargly goop, but that's encrypted, and it's encrypted in transit with TLS, but it's encrypted at rest with this AES 256-bit CBC key that Vault is managing. And Vault is being run outside of Kubernetes right now. So even if you were to compromise this etcd cluster, you can't actually decrypt this data by anything other than a brute force attack. And all of this is open source, and there's a ton of guides and documentation and blog posts out there, including these slides, which will be up on the internet shortly, that'll help you get this stuff set up. So to conclude, Kubernetes can take us from sad to happy with respect to secrets management. Use at least 2 layers of encryption, application layer encryption and hardware layer encryption. Rotate your keys regularly. Leverage envelope encryption. It's the fastest and most scalable way to do data encryption that we have today. And protect Kubernetes secrets using an external KMS provider, whether that's a cloud provider or something like HashiCorp Vault. Thank you. I'll go back because there are people taking pictures of this slide.
So are there any questions?
Hello. So what if I run etcd on the master nodes? That means that I basically need to provide IAM permissions for the master nodes, and then if I compromise the master, basically I can decrypt anything by knowing the key ID, if it's KMS, for example, right?
Right, so the question is, if I run etcd on the same nodes that I run the Kubernetes API server...
So this model suggests us not to run etcd on the same nodes, like on the master nodes, right? So we need to decouple to have maximum security.
Yes, that would increase your security much more than running them side by side.
Okay. But do you have any suggestions what to do if I have etcd running on my master nodes, and basically to use Amazon KMS or Google KMS, I need to provide a service account integrated into machine's metadata, right? Or IAM role integrated into machine's metadata. What can I do to increase my security?
So even if you use an external KMS provider, when etcd is on the master node with the Kube API server, you've still increased your security from when the keys live in plain text, because you can revoke that service account and those credentials without taking down all of your production infrastructure. And also, an attacker can't decrypt your data offline. So you've increased your security posture a little bit, because in the previous model where the keys are just stored in plain text, an attacker can just do a full file system dump, and now they can run away with your data and decrypt it offline. Whereas with the KMS provider, if you have some audit logging and those things set up by default, if you detect some anomalies, you can revoke access to that key, and now an attacker can't decrypt that data because you've broken the link to KMS. So that's really the only thing. If you haven't separated etcd from the master nodes, that's the only thing you've improved, is the ability to revoke access and prevent offline decryption.
Okay, thanks.
Other questions? There's no other questions? Okay.
Hey, thank you for the talk. Okay, so for example, I have a huge Kubernetes cluster for 1,000 nodes and have a lot of data on etcd nodes. But if I want to change my KMS key or whatever, so should I re-encrypt all this data? How is this process going on?
Yeah, so the question is, what should I do with my existing data that may or may not be encrypted in etcd? When you generate that encryption provider config, let me pull up a slide that has one on it. So providers is an array. The first item in that array is what is used to encrypt all data. Everything else is tries to decrypt the data. So there's one of them called identity, which just takes an empty object. That will allow you to decrypt all of the plain text objects that you currently have in etcd. Then you can do a kubectl replace all on all of your secrets, and it'll take a little bit if you have 1,000 nodes, but it'll go through and encrypt them all. Alternatively, you can just choose to just choose to encrypt things going forward, and how, you know, if you rotate your pods